Welcome to Spring LIB.
For this question, we are asked to explain why an sp3 carbon-chlorine bond would be more polar than an sp2 carbon-chlorine bond. We are also asked to rank the following structures by their boiling point. Now, to answer this first question, let's take a look at sp3 and sp2, what that means. An sp3 hybrid orbital means that it's like 1 part X and 3 parts P. An sp2 orbital would be 1 part S and 2 parts P. So we see 75% P character, 25% S character, whereas in sp2 you'd have 33% S character and 67% P character. Now, let's think about what these orbitals mean, what they look like. So an S orbital is a sphere, and those electrons are held tightly, they're held close. P orbitals are more spread out. The electrons are better able to move away from the nucleus, and so we're able to see a more polarized bond where the charges separate from the positive nucleus and the negative electrons. They can separate more than they could in an s orbital. Now, since an sp3 carbon-chlorine bond is much more p character than an sp2, we can see greater separation here, more ability for that to polarize, and so we see that making a more polar bond. For question B, to rank the following by boiling point, we'll be using some of that information that we just logicked through in part A. But first, we can compare these. They all have the same length of their carbon chain. All of them have 6 carbons, so that doesn't tell us anything. But they have different halogens. Bromine is larger than chlorine, and we know that the larger, more polarizable halogen corresponds to a higher boiling point. So we could compare these two and say that bromine is going to have a greater boiling point than the chlorocyclohexane. Comparing the two on the right, we have sp3 hybridized carbons all around, and sp2 hybridized carbons all around. Now, from part A, we determined that an sp2 carbon has a less polar bond. And for that to be less polar, that means there's less difference in charge, which makes for a weaker attraction between molecules, which hold them together, and that's what impacts your boiling point. So since we have weaker interactions between the chlorobenzenes, we know that this is going to have a lower boiling point than the chlorocyclohexane. So we can rank these structures with the bromocyclohexane being the first, chlorocyclohexane being the second, and chlorobenzene being the third. We can always look up boiling points to confirm our analysis. It's always good to do that after you do your analysis, just to check, just to make sure that you understand why things are, but you can always check your answer. So by just looking this up, I found these were the actual boiling points. And that's how we know for sure our analysis was correct.